How do you visualize data? Let me tell you a story. So I was doing an honors thesis and the data analysis got to be really complicated. And so I sought out the statistics department. And I got to meet with somebody who I'd been taking a class with by the name of Dr. Scalia. But we called him Boots, because he always wore boots. If you ever see him, you can call him Boots, from me. So I brought my data set to him and asked him if he could help me analyze it. And I thought, this was the moment. This is when I would see a stats Jedi in his element. And I really wondered what it would look like. Like I envisioned it was like Neo in the Matrix, looking at data and just interpreting insights that nobody else could see.
All I see is blonde, brunette, redhead.
But then he plotted my data. And I was like, what? That's it? Yeah, he just plotted the data, which is something that I could have done. And it didn't require any training at all for me to see what was going on. And I had no idea what I was doing. And the more advanced I get in my stats understanding, the more I realize, yeah, we tend to make things more complicated than they need to be. Most people can understand what data are saying if they just look at a graphic. In fact, there was a paper that showed just that. This paper demonstrated that people without any sort of statistical training could interpret data if they just looked at a graphic. So in this video, I'm going to show you the very basics of interpreting plots and how to glean insights about your data from plots. This video is basically based on a paper that I wrote called Visual Partitions. If you want any more details about anything that I'm talking about, you can read that paper, but it is on the more technical side. And by the way, as an aside, I know most of my audience is not super sophisticated. I know most of my audience is learning statistics and they're not like diehard statisticians, so this paper that I wrote is a little more on the technical side. So some of you might benefit from it. Some of you, it might go over your heads, and that's okay. And in this video, I'm going to be using FlexPlot, which is software that I developed in R. And throughout this video, I'm going to show you the code that I use to generate the plots. And I'll even upload the R script that I use online. But to do this, you don't have to know R. You could also do all this in JASP and Jamovi, if you prefer a point-and-click interface. So let's talk about the simplest case. Simplest case being you have one variable you're trying to visualize. We would call this a univariate plot. So we have two types of plot. One is called a histogram and one is called a bar chart. Histogram is for numeric variables, bar charts is for categorical variables. And in both cases, X represents the value and Y represents the frequency. So this just tells you how your scores are distributed, or it tells you how many scores fall at particular locations. And if you want more information about interpreting these sorts of plots, see the video linked in the description. Now let's make it a little more advanced and do bivariate plots. With bivariate plots, you have the predictor on the x-axis and the outcome on the y-axis. This plot shows a numeric predictor and a numeric outcome, and this shows a categorical predictor and a numeric outcome. And I'm not going to review any time where you have a categorical outcome for reasons. Long story short, those models are a lot more complicated and we should be using generalized linear models. I'll link a video description about generalized linear models if you're interested. So for these plots, all we're looking for is a slope. Like in this plot, we have a positive slope. And this applies for categorical variables too. So if you look at this plot and you imagine a line connecting the two dots in the middle, you have a slope. Easy peasy. So anytime you have a non-flat slope, that indicates there's a relationship between the variable on the x-axis and the variable on the y-axis. Conversely, if there is no slope or the line is flat, there is no relationship. And if you need help remembering that, just remember this mnemonic. If you're on a date and the conversation is flat, there's no potential for a future relationship. If we're looking at a bivariate graphic, especially if we have a numeric predictor, there are certain things we want to look out for. In particular, we want to look out for curvilinearity. Now, there's actually lots more problems you should look out for, and I will link a video in the description to help you identify what kind of problems to look out for. But for this video, I'm just going to talk about curvilinearity. But we particularly need to look out for curvilinear relationships because that dictates the type of model that we ought to choose. And hey, there's another video that I just made. Ha! I will link that in the description on modeling nonlinear effects. So that covers univariate variables as well as bivariate relationships. Now, what happens if you have two predictor variables? We're going to use a strategy called binning. Binning basically just means that you separate one of the variables into like high, medium, and low. And by the way, you won't do this. R will do it for you in the background, but just so you know what R is doing. And so here's an example here where we've got two predictors, Z and X. And X, even though it's numeric, it's been categorized into three groups. These numbers right here give you the value ranges, but we could just refer to this as low, medium, and high. And instead of showing the different bins and panels like we have here, we could also overlay them on the same plot and use different colors, lines, and symbols to identify the three different groups. Now, if you have two predictor variables, you might be wondering, all right, which variable do I put on the x-axis and which variable do I put in panels or in rows and colors and panels? Well, usually what I do is whatever variable is more interesting to me, or what I would call the interest variable, the one that I'm hypothesizing about. And the one that is bend is the one that I call the covariate, or the thing that I'm not really interested in that I just want to control for. Alternatively, you could view it both ways. So you could do one plot where x is on the x-axis and another plot where z is on the x-axis, because sometimes it just doesn't matter. In these plots, we interpret it very similarly to the way we did before, where if there is a slope, it indicates there's a relationship between y and whatever variable is on the x-axis. Now, what about the other variable? The one that's paneled, or the one that's in different colors or lines or symbols or whatever. The way to know if that has a relationship with the outcome is by differences in intercept. So if you look at this plot right here, you can see that the blue line has a vertical shift relative to both the green line and the red line. Or in other words, they have differences in intercept. This tells you that whatever variable is represented as different colors here has a main effect with y. Or like I said, you could just flip the axes. So in this plot, we have z on the x-axis, but we could also put x on the x-axis. So obviously it's a lot easier to tell whether there's a relationship and the nature of that relationship if you put it on the x-axis. But also, like I said, you could tell by differences in intercepts. Now these plots can get confusing because you have 3 panels to interpret at once, or 3 different colors to interpret at once. An alternative to this is what are called added variable plots. The basic idea behind added variable plots is first, we fit a model predicting the outcome from the covariate. Then after we fit that model, we residualize that, which means we take the predicted score and subtract it from the actual score. And that's called a residual. And this residual represents the outcome after subtracting out any sort of linear association with the predictor variable. And then once we have those residuals, which again have subtracted out that covariate, then we can plot our other variable against those residuals. And this plot will show you the relationship between your new predictor variable and the outcome after subtracting out the effect of the covariate. So if we're interested in the relationship between one variable and another after subtracting out the effect of another variable or after conditioning on another variable, then an added variable plot is just the graphic we need. And so here's what the relationship looked like as a paneled plot, which in some ways is unnecessarily complicated. And here is the added variable plot version of that. And so added variable plots are really a simplification. They allow us to look at these more complex relationships using just a simple graphic. However, added variable plots have one major weakness. They cannot be, or they should not be used when you have an interaction in the model. And an interaction means the relationship between one independent variable and the outcome depends on the level of another independent variable. Let's look at an example. Here we have an example where the relationship between z and y totally depends on the level of x. So for low levels of x, it's negative. For medium levels of x, there is no relationship. And for high levels of x, the relationship between z and y is positive. We would call this an interaction effect. And you may not be surprised to learn that how interaction effects show up in visuals is by non-parallel lines. Or in other words, if you have non-parallel lines, you have an interaction effect. So let me just say again, you should not use added variable plots if you have interaction effects. Why? Because added variable plots show you the main effect of a variable. But if there's an interaction, the main effect doesn't even make sense. Like in this plot, the main effect or the average effect of z, right? Yep, z, is 0. On average, its slope is 0. But we know by looking at the graph that that's an oversimplification. That its relationship is negative sometimes and positive sometimes, and it totally depends on the level of x. So for this reason, you should never use an added variable plot that shows just a simple bivariate relationship because, again, it's going to depend on the level of the third variable. So in this case, if you have an interaction effect, you have to use paneled plots like these, or you have to use colored plots, I guess is what I can call them, like these. Now let me address a myth that drives me absolutely nuts. I don't know where this came from. I don't know who started this myth. But whoever started this myth is going to have to answer to the statistical gods. I've heard people say that for interactions, the lines have to cross, and if they don't cross, it is not an interaction. That is false. Let's look at an example. So here, none of these lines cross. And so some people, I don't know why, they would say there's no interaction here because the lines don't cross. That is absolutely false. Again, there is an interaction if the lines are not parallel. That's all that matters. Doesn't matter whether they cross. And I guess a technical side note, if you extend those lines into infinity, they will eventually cross. So I guess there's some rationale for it, but yeah, forget about the crossing thing. Because most variables don't go to infinity. So yeah, it's a weird rule. I don't know where it came from. So let me just summarize. If the lines are parallel, you can visualize each variable's relationship using added variable plots. And you could interpret those with complete freedom. You're not going to miss out on any important insights by doing this. If they're not parallel, however, you do have to visualize them as paneled variables or as colored plots. In a multivariate plot, basically. Okay, technical side note. So, by the way, this has nothing to do with the rest of this, but I just use the word multivariate, and some people might bark at me for using the word multivariate. So if you're a statistician, multivariate means you have multiple dependent variables, but for everybody else in the world, multivariate means multiple predictor variables. And because most of my YouTube audience are not statisticians, I use the word multivariate to refer to multiple predictor variables. And so I know it technically means multiple dependent variables, but if we had a word for multiple predictor variables, I wouldn't be abusing the terminology, but we don't. I mean, there's multiple regression, which refers to multiple predictor variables, but what if you have multiple numeric and categorical variables? Then it's technically not multiple regression anymore. What do you call it then? I don't know. I just call it multivariate. So hopefully that satisfies the pedantic. Now, let's say we want to visualize 3 or more predictor variables. What do we do then? We cry. We scream and we cry. Not really. Chances are when you saw that, you panicked a little, and it's okay. It's okay to panic. I'm here to help. Yeah, I get it. Looking at these sorts of plots can be information overload. So FlexPlot can visualize up to like 5 variables at once. But anytime I'm visualizing lots of variables like this, my goal is always to try to simplify these plots as much as possible. And so to begin my process of simplification, what I'm looking for are 2 things. One is evidence of nonlinearity. And so in this example, instead of using lowest lines, which is the default, I decided to use quadratic lines because lowest lines are super sensitive to outliers, especially in the tails. And so you tend to get plots that look like that, where there's a little dip just at the very end, but not in the middle. And so in those situations, that's probably just outliers that are dragging the lowest line up or down or whatever. Whereas the quadratic lines are less sensitive to that. But anyway, I plot the quadratic lines and then I look for consistent nonlinearity. If I see evidence of nonlinearity, then that tells me I need to pick a model that can model nonlinearity. And again, if you want to know how to do that, see the link in the description. But the other thing I look for is number 2, evidence of non-parallel slopes. That's really the primary thing I'm looking for, is non-parallel slopes. Because if all the lines are parallel, like in this plot, then that tells me I probably don't need to visualize all these variables at one time. I could just use added variable plots for each of the individual variables. Although probably what you should do is alternate which variable is on the x-axis and kind of play around with it, because sometimes you can have an interaction between the row panels and the column panels, and you wouldn't be able to tell unless you put one of those on the x-axis, so make sure you're doing that. But assuming you don't find evidence of interactions, then you could just visualize all 3 of these with an added variable plot, and you're good. But what if you have non-parallel lines? Then do you have to interpret these massive plots? Not yet. Instead, you could use another tool that I call marginal plots. This is something I believe I invented. I haven't seen anybody else talk about this. So if we see evidence of nonlinearity, what we want to know is x1 interacting with x2, or is it interacting with x3, or is it interacting with a? Well, one way to tell if it's interacting with a is to look at the different colors and say, are the different colors basically parallel? And for the most part, they are. We have some deviations like here and like here, where they're not precisely parallel, but they're probably close enough. So it's pretty safe to say that x1 is not interacting with a. So now, if we want to figure out whether it's interacting with x2 or x3, what we can use is marginal plots. So here's an example of a marginal plot. So these top 3 plots here are basically visually averaging these plots here for that one, and these plots here for that one. So it becomes a visual representation of the relationship between x1 and x2 averaged across x3. And if you look at this plot, notice that the slopes are roughly parallel. They're not perfectly parallel, but they're pretty parallel. So that tells you x1 is probably not interacting with x2. On the other hand, if you look at the right plot, those slopes are definitely not parallel. So again, this bottom plot shows the relationship between x1 and x3 averaged across these 3 rows. This one shows it averaged across these 3 rows, and this one shows it averaged across these 3 rows. And we notice that the slope consistently changes. It goes from negative to basically flat to positive. This very clearly tells us that x1 and x3 interact with one another. So it interacts with x3, but it doesn't interact with x2. So what do we do at this point? For this particular data set, this tells us that we have to visualize x1 and x3 together. Why? Because again, there's an interaction there. Because you can't talk about the main effect of x1 or the main effect of x3, because the main effects depend on the level of the other variable. So you have to visualize them together. So we could do a plot that looks like this, which is much simpler to interpret than the multi-panel plot that we had earlier. This tells us that for low values of x3, the relationship between x1 and y is strongly negative, whereas for moderate levels of x3, the relationship is slightly positive, and then for high levels of x3, the relationship is strongly positive. And what about the remaining variables, a and x2? Well, assuming that x2 and a do not interact, or x3 and a, and in this case they don't, then these two relationships can be simplified with simple added variable plots. So here's a relationship for a, and here's a relationship for x2. So we went from this massive mess to these 3 simple plots that can be interpreted in isolation. That's much easier to interpret. So let me just summarize. So we started with these multi-paneled plots that were a little overwhelming, but we were just looking for evidence of non-parallel lines so that we could then simplify it. So you might be asking yourself, hey, so you might be asking yourself, are these multi-paneled plots ever necessary? Or can they always be simplified? And unfortunately, they can't always be simplified. So sometimes you need those multi-paneled plots if you have a 3-way or a 4-way interaction. And I would suggest you pray to the statistical gods that you don't ever have a 3-way interaction, and you don't ever have a 4-way interaction, because it's really hard to wrap your brain around 3 or 4-way interactions. But if you do have a 3-way interaction, remember this insight. Remember that a 2-way interaction basically means that the main effect of one variable changes depending on the level of the other variable. And likewise, a 3-way interaction means the nature of a 2-way interaction changes depending on the level of a third variable. So let's look at an example. So here we have the relationship between symptoms, medication, gender, and ADHD. And that is a lot to interpret, and that is overwhelming, and that's okay. But let's go ahead and break this down a little bit and try to simplify what's going on here. Let's just look at the male panel. What is this telling us? This tells us that for those who have ADHD, taking Adderall reduces their symptoms a ton relative to those who do not take Adderall. Or in other words, Adderall is effective at reducing ADHD symptoms if you have ADHD. On the other hand, if you do not have ADHD, it has the opposite effect, that it makes symptoms much worse relative to people who are not medicated. And this is pretty well known. If you take Adderall and you don't have ADHD, it's basically like taking speed. But if you have ADHD, it calms you down. So that right there was just a simple 2-way interaction. And it might take some mental gymnastics to understand what's going on, but it's not that hard. Now, what is a 3-way interaction? Again, a 3-way interaction says that the 2-way interaction changes depending on the level of a third variable. And so now let's look at the other plot. So that was the male plot that we looked at. Now let's look at the female plot. And what do we find? We find the exact same relationship, that if you have ADHD and you take medication, it reduces symptoms. If you do not have ADHD, then it makes things worse. However, notice the female plot, that effect is much smaller than it is on the male plot. Now, I don't actually know if this would actually happen in reality. I'm just making this up, but you get the idea. So again, a 3-way interaction means the nature of the 2-way interaction changes depending on the level of the third variable. So how do we identify 3-way interactions from these multi-paneled plots? That is a good question. But I'm not going to tell you the answer. I'm going to save it for the next video, because in order to do that, we have to introduce a new tool. And I'm too lazy to do it right now, so we're going to wait. This has been a very, very brief introduction to visualizing data. And in the process, I've had to assume that you have some foundational knowledge. If you're missing that foundational knowledge, or if you want step-by-step guidance in getting to the point where you can interpret these sorts of data, I invite you to visit simplistics.net. And on simplistics.net, I have developed courses. And these lessons guide you through step-by-step every process in data analysis. These courses are designed to teach you to make sense of your data. So if you find yourself struggling with data analysis, struggling with interpreting p-values or estimates or plots, or if you feel like you're just missing something from your data, please visit simplistics.net, where you can have live classes with personalized instruction from me, or you can do self-guided classes where you get to learn on your own. And from these classes, you will become a statistical Jedi, and all your statistical dreams will come true. And it will lead to peace and happiness forever and ever. So the question is, are you ready to be happy? So I hope to see you at simplistics.net, where we can be friends and stuff and hang out and have stats parties, because that's what statisticians do. They have stats parties, apparently. But what do I know? I don't have any friends. So, yeah, with that, peace out.